And so how does it? Okay, here it is. So today we will describe the current problems encountered by missions of ESA for the mathematical community to solve. We will talk also about the space missions that challenge the edge of current mathematical optimization methods. And we'll also describe the efforts on the analysis and assessment of global optimization techniques and the description of future activities of the development of a global optimizer. So the European Space Agency has been using mathematical optimization for space missions since the 80s, the early 80s. And along the years, several mathematical solvers have been funded by ESA with the purpose of optimizing space trajectories, spacecraft control algorithms, spacecraft building and testing procedures, as well as spacecraft structures, and of course, the combination of all, which is the multidisciplinary mathematical optimization. Of course, most of them were quite successful, some less, but here we're gonna talk about and sort these out. So, so the context of this talk today, where we'll start with a short introduction of the European Space Agency and then of the flight vehicles and air thermodynamics engineering section, which is the section that I'm working in. And then we will talk about the ESA mathematical optimization interest and the multidisciplinary optimization for flight vehicle engineering. We will then talk about the ESA space missions as promised and the mathematical optimization challenges, and we will conclude with future activities and possibilities for future collaborations. So we are ESA. So I would like to start with a short introduction of ESA. So there are 22 member states, as you know, and more than 5,000 employees. There are 3 associated members and 5 or 6 cooperating agreements with other countries aside from the 22 member states. So for the why, what do we do at ESA? Why do we do it? We do it for the exploration and use of space for exclusively peaceful purposes. Where? So ESA, the headquarters are in Paris, but there are 7 other sites across Europe, and of course the spaceport in French Guiana. And the idea of an independent European space organization was actually developed in the 1960s. 2 existing organizations at the time, which was the ESRO, for space research and ELDO for launchers, were merged in May 1975 to form ESA. And now we ask how much. So actually 85% of ESA's budget is spent on contracts and industry in ESA member states. And citizens of Europe can enjoy the results just for 12 euros per European per year. So what do we do in ESA? Unlike many national space agencies, ESA actually covers all of the activities from space science, human spaceflight exploration, Earth observation, space transportation, navigation operations, and space safety, technology and telecommunications, and of course, active industrial development. This makes ESA very unique. Also, we have the spaceport in Kourou, which means Europe has an independent access to space for scientific and commercial missions, autonomous operations and space safety capabilities through ESA's Missions Control Center. Yeah, so ESA has developed more than 80 satellites that were tested and operated since 1975, and more than 22 launchers from Europe Spaceport in Kourou. So it all started, as I mentioned, in 1975 in the signing of the ESA Convention with only 10 member states. And now there are, as I mentioned, 22 member states with 6 additional cooperating countries, which could be also outside of the EU. So for instance, Canada also has a cooperating agreement with ESA. So what is the main challenge here? So we are facing two challenges. One is to explore the universe and improve life on Earth for exclusively peaceful purposes. So the member states or the cooperating agreement countries could be imagined as a group of explorers preparing for a long, harsh journey. So this journey is going to take us around the Earth and into and deep into our universe. So again, the main two challenges: to explore the universe, improve life on Earth, and doing that while serving peaceful purposes. So ESA has establishments spread out all over Europe, where the headquarters are in Paris. ESRIN, which is in Rome, is mainly for Earth observation. ESTEC, which is where I work in currently, is the Research and Technology Center in Nordwijk. ESOC, which is for space operations in Darmstadt in Germany, and EAC for this is the Astronaut Center in Cologne, Germany. ESAC is for Space Astronomy Center in Madrid in Spain, and Harwell in the UK. There's also RIDU, which is in Belgium. Where there's the European Space Security and Education Center, as well as ESA Ground Station Network. And of course, the spaceport in French Guiana, which I have mentioned before. In addition to that, there are more premises and offices, of course, in Brussels, in Washington, in Moscow, and spread out in the US. So for the ESA programs, all the member states participate in mandatory programs. So in the activities related to space science and a common set of programs. And these mandatory programs are coming from the general budget, and they include future studies, technological research, education, and common investments, as well as science, so solar system sciences, astronomy, and fundamental physics. The optional programs that each country could choose of its own which programs they would like to participate in are human spaceflight, telecommunications, and integrated applications, Earth observations, launchers, navigation, robotic exploration, and space situational awareness. So how we look at these collaborations with the countries. We look at it as this, here, as you can see on the right, is the Innovation Triangle Initiative, which this triangle actually illustrates the concepts that is behind the close collaborations between the three parties that are involved. So the inventor, the customer, and the developer. And this is all a must for the rapid, successful introduction of breakthrough technology innovations in industry. So the same for the analogy of the innovation triangle, we see the same thing for ESA and its partnerships with industry and academia. This is all a part of a function for success. So a bit of the flight vehicles and aerothermodynamics engineering section, and what do we do there? So we are the focal point for the architecture, design, analysis, and technical assessment of space transportation vehicles for suborbital, orbital, and exploration applications, including upper stages, re-entry, expendable, and reusable vehicles. We do the overall feasibility and viability assessments, as well as quick design iterations, with the support of the necessary tech competences. We also do the coordinations and of the specialized and provide support in R&D initiatives with other tech sections. And we provide engineering support, research and development and testing activities related to flight vehicles, flight physics, aerodynamics, thermodynamics, and fluid dynamics engineering, as well as architecture, design, and analysis of suborbital re-entry space transportation and exploration vehicles. The activities of the Tech MPA section, or the Flight Vehicles and Aerothermodynamics Engineering section, are based on 4 main pillars. The first one is the flight vehicle engineering that includes ascent, cruise, and re-entry, and also into other planetary atmospheres. as well as plume analysis, multiphysics, and multiphysics modeling. The second pillar is more related to fluid dynamics and ground testing and ground-to-flight transportation methods, as well as fluid structure interactions. And the third one is the exploration of flight data from flight experiments, especially involving aerothermodynamics and re-entry. And the fourth pillar is the computational facilities and flight physics modeling tools, which includes the test facilities in propulsion, aerothermodynamics, and flight physics. So we also provide support to projects in four main areas. The first one is, of course, flight vehicle engineering, which include vehicle performance, multidisciplinary design, and fast and multi-physics design loop. We provide support also in the assessment of variability investigations. So that includes quick and accurate modeling and simulations of aerodynamics, fluid dynamics, and contamination. We also provide support for testing and verification, testing of aerothermodynamics in flight vehicles and in external facilities. These are facilities that we don't currently have at ESTEC, but as well as visualizations of missions and performances. We also provide support for post-flight data analysis. So after the flight, after the mission, in comparison with the predicted versus the actual flying qualities. As for the activities that we are currently running in the section are mainly these 9 topics. So again, flight vehicle engineering. We have a lot of activities concerning decelerators, design for demise, which is the design of a spacecraft in such a way that it will disintegrate within the atmosphere upon re-entry. Of course, aerodynamics, technology and test beds, post-flight analysis, thermodynamics, fluid dynamics, and contamination. So these are all activities that we are currently running in the section. So that concluded my short introduction about ESA and the flight vehicles and aerothermodynamics engineering section. I will now go back to our original topic, which is the optimization. So at ESA, the mathematical optimization interests are presented here as follows. So ESA is interested in nonlinear, mixed integer, stochastic, heuristic, constrained, optimal control, dynamic programming, multi-objective, multimodal, and evolutionary optimization. We are not interested in linear programming, pure mathematical modeling. Yeah, and that's it. Sorry. So the interest of ESA in optimization methodologies and challenges that are that can be tackled within the ESA missions could actually be either continuous or discrete, depending, of course, on the mission. Within the continuous, we have constrained and unconstrained. It could be also multi-objective, non-linear constraint, and within the unconstrained could be global optimization, non-linear least squares, and non-differentiable. Also, we look at discrete problems, so stochastic and integer. As for the mathematical optimization methodologies, they could be categorized as branch and bound or other methodologies. For the branch and bound, basically how this works, that there is a set of candidate solutions forming a rooted tree. The algorithm then explores the branches, which are subsets of the solutions, and the branch, each branch is basically checked against the estimated bounds and is discarded if it cannot provide a better solution than the previous already found. So within the branch and bound methods, we have the mixed integer, the DC, and the interval. And we, of course, also look at other methodologies, which include genetic algorithms, simulating annealing, and stochastic methodologies. Now, I want to talk about a bit of multiphysics design because multiphysics optimization is something that we do quite often and quite a lot in our section. So it is mainly dominated by tightly coupled interactions between key engineering disciplines. So as you can see here, all the disciplines that are used for multi-physics design. We have the performance, the propulsion, aerodynamics, mass and structures, and navigation and thermodynamics, and they're all part of multi-physics design when we design a spacecraft or a launch vehicle, or any flight vehicle, actually. So the multiphysics approach recognizes the importance of a tight interaction between all of these subsystems that I've mentioned. So how do we do it actually? So we are looking at multidisciplinary optimization for flight vehicle engineering. And we look into these four main disciplines: the structures, performance, aerothermodynamics, and propulsion. So as you can see here, sorry, my pointer is on the wrong slides. As you can see here, multiphysics design actually requires less computational costs as we tackle less number of disciplines, and also the fidelity is lower than high fidelity design, of course. So this classic long loop is very slow and computationally costly. And the multi-physics design approach is more efficient, fast, and provides a fast multi-physics design loop. The optimal co-design allows to depart from a good optimized first iteration. So if we consider a rocket, for example, so the computer of the rocket would be usually placed here, and this computer would be responsible for the mission vehicle and mission vehicle management. So the design of the rocket itself would be done by the flight vehicles engineers, and they are needed for the design of this rocket, while the software engineers are basically needed for the commands themselves and the onboard software, the motherboard software that is responsible for all the commands and basically the operations of the rocket itself. But all of this could not be done without the foundation that is provided by mathematics. So the main building blocks of this would be the solvers, propagators, integrators, and optimizers, that they are the building blocks for the design and optimization, basically, of every launch vehicle. So the main conclusion of the main message I'm trying to convey in the slide is that mathematics play a fundamental role in flight vehicle engineering and any design of any flight vehicle or a rocket or a spacecraft, actually. So what is MDO? We found this definition by Timothy W. Simpson. MDO is the multidisciplinary design optimization. So it's a methodology for the design of systems in which strong interactions between disciplines motivates designers to simultaneously manipulate variables in several disciplines involved in the coordination of multiple disciplinary analysis to realize more effective solutions during the design and optimization of complex systems. So what we're looking here is, as I mentioned before, and I will explain it more in my next slides, is basically, the interactions between several disciplines or several subsystems to do the overall optimization of the complex system. So if we look at the MDO environment, If we look at the MDO environment, here is a system that represents the spacecraft. And we have all of these different subsystems, so aerodynamics, propulsion, the actuators, the heating, performance, the sizing of the entire system, weights, operations, and costs. So all of these subsystems would have to be taken into account. And between all these subsystems, which is the great emphasis of multidisciplinary design, is that they all affect each other, and there is a tight interaction between every subsystem that we would have to consider. So the aerodynamics affects, of course, the propulsion and vice versa. and it all has an impact on the system itself. Of course, the cost, the operations, the mass, and the performance, of course. Sorry, doesn't stuck. Okay, here it is. So if we go back to our launcher, the rocket case. So in this case, we want to consider the entire vehicle design optimization. So we want to do the stage sizing, the geometry optimization, the aerodynamics computation, the propulsion system sizing, and the structural loads and model analysis. Our goal is basically to do the mission analysis and the trajectory optimization while optimizing all the rest of the subsystems that I've mentioned to reach the final goal, which is the optimized trajectory. We would also look at the mission-specific flight path optimization. And here you can see an example of optimized trajectories for a particular rocket. That here you can see we had to look at the heating, the heat load of the rocket upon its trajectory. So this is just a quick example of an analysis that we've made. So continuing with this example, here we look at the optimizable parameters which we want to ultimately optimize. So that would be the chamber pressure, the expansion ratio, and the throat area, as well as the mixture ratio within the engines. This would result in the aerodynamics area of the vehicle, and as well as in the thrust and mass flow resulting from this. From here, you can see the equations of the simplified equations of the analysis that is made. So all of this would result, of course, in the aerodynamics reference area, as well as the propulsion system mass and the thrust and mass flow. And all of these are parameters that are needed for the trajectory, well, first the simulation and then the optimization. So this altogether is an iterative process which involve the trajectories, the propulsion, the structures, and the aerodynamics in the same loop. The output ultimately would be the optimized subsystems that are tightly intact between themselves. And this is applicable for expendable launchers, reusable launchers, and re-entry vehicles. So how does the MDO process works? Usually we would start from the propellant system definition. Sorry, I get confused with the screens all the time. So we would usually start with the propellant system definition. This would give us the thrust, then the propellant type, and the shape design, and these two will impact the mass, of course, and we'll have, and obviously we will have some to constrain it in either boundary or path constraints. Then the shape design will result in the aerodynamics, where here we would like to optimize the L/D force, well, depending on the mission, of course. This will also, the aerodynamics will result in heat, aerodynamic heating, which will require the design of the TPS, and as a consequence, also the structures and the GNC, which will basically, and the GNC is, well, it's the altitude control. So all of these components that are co-designed will ultimately result in a trajectory and provide us with the first guess. So as I mentioned before, this is an iterative process. So after we have the initial first guess, the iteration would continue on because these all subsystems are interacting with each other, have interactions with each other and affect each other. So this iterative process will continue till we find the optimal solution. and the optimal trajectory, as well as the optimal subsystems for the wanted desired results. So here in a bit more details, the work methodology starts from the trajectory and from the mission definition, as well as the reduced level model, as you can see here. So we have the propulsion, the mass and the materials and structures, the thermodynamics, and the GNC and the costs. These reduced level models are actually dependent on a higher fidelity models that could include the cycle program, maybe a CAD model for the structures and the materials, a CFD, or using solving Navier-Stokes equations for the more simplified model for the air thermodynamics, and so on. So this is, again, an iterative process between also the reduced level and the more high fidelity, or let's say a specialist subsystem level. So back to the optimization question, and why is it important for ESA? So the optimization is actually appearing everywhere in flight vehicle engineering and in all ESA missions. So we look at the performance in the position and attitude control, the control of large structures, power and thermal control, and as well as control of mechanisms. It is constantly solved and resolved by new groups, and different groups within ESA would formulate the optimization problem different than let's say Group B will formulate it different than Group A. And a good amount of time and funding is dedicated to solve optimization problems, mainly on dynamic systems that have multiple phases and continuous dynamics, and that are separated by discrete transitions. So now I'm going to talk more into details about the ESA missions and the optimization cases and challenges. So the ESA missions are actually divided into 4 categories. The first one is science and exploration, which includes the space science missions and the human and robotic exploration. The second one is applications, which includes Earth observations, telecommunications and integrated applications, and navigation. The third one is enabling and support, which includes space engineering and technology, as well as space transportation, and safety and security, which includes space safety. So the first missions I'm going to talk about are JUICE and Cheops. So JUICE is the Jupiter Icy Moons Explorer, and it is the first large class missions in ESA Cosmic Vision from 2015 to the 2025 program. It is planned to launch in 2023, so quite soon, and it will spend at least 3 years making detailed observations of the giant gaseous planet Jupiter and its 3 largest moons, Ganymede, Callisto, and Europa. Then for Cheops, this is the Exoplanet Hunter, and it stands for characterization of exoplanets satellite. It is the first mission to be dedicated to studying the bright nearby stars that are already known to host exoplanets. And the idea is to make high precision observations of the planets and size its passes in front of its host star. So the challenges that we face in these 2 missions are, first of all, for JUICE, is to visit, or the problem, let's say, is to visit all Jupiter moons in minimum time with minimum fuel and maximum payload. And the need is the optimization of interplanetary trajectories. The current solution is nonlinear programming, local optimization by segments, and there are actually more than 200 segments for the entire trajectory currently of JUICE. And what we're looking at, or the challenge that we want to pose, is the global optimization of the entire trajectory for JUICE to visit the planet and its moons. Then for the second mission, for Cheops, sorry, The problem is to discover the planets by surveilling the traces of bodies in front of their sun. The need is in ultra-high pointing accuracy and optimal control. Currently, the solution is to cascade of PID controllers, and the main challenge that we would like to pose is the robust optimal control. Then if we go to the next slide, sorry. Okay, here it is. So for human exploration, we are looking at two other missions. So now with the Artemis initiative and going back to the moon and to Mars, we're looking at two main challenges for the human exploration. The first one is the lunar lander, as we would like to land humans on the south pole of the moon with high accuracy. And the second is sending humans to Mars. So the idea is, to bring humans to the red planet. And now it's stuck. Okay, here it is. So, okay, so the problem for the human lunar lander is to land on the moon in the South Pole, as I mentioned, with accuracy of 50 meters. The need is absolute and relative navigation and, of course, the robust control. Current solution, there is none, and the challenge that we would like to pose is the robust navigation, the data fusion, and the advanced optimal control. As for the Mars, bringing humans to Mars, other than bringing the humans to Mars, we would also have to land a crew of 3 on the Martian atmosphere. The need is, of course, the soft landing, and the current solution, well, there is none. The challenges that we're looking at are hypersonic real-time guidance, data fusion, and optimal control. As for robotic explorations, there are 3 missions that we're looking at. One is the asteroid impact mission that is called AIM. And AIM, main aim was to travel to a binary asteroid system to perform high-resolution visual, thermal, and radar mapping. And this was also in the frame of NASA's DART mission, which was aiming to collide with one of these asteroids. Now this mission has actually been improved and is called HARE. The second mission that we're looking at is the Phobos sample return mission. So Phobos is one of the Martian's moons, and we're looking to bring back a piece of Phobos, as well as for the Mars sample return missions, which an ultra high accuracy landing on Mars is needed. The problem that we pose for these 3 missions are first the touch and sample of an asteroid. For that, we would need relative navigation and robust control, and currently there is no solution. The challenge is, of course, optimal real-time landmark recognition. As for Phobos, to bring a sample from Phobos to Earth back, for that we would need to drill, and so for that we would need robust navigation and control. Currently, there's no solution, but the challenge that we pose is the optimal control and the real-time trajectory optimization. As for the Mars return sample, so to land a heavy payload with ultra-high accuracy on Mars, the need is the hypersonic real-time guidance and the robust control. There is currently no solution, and the challenge that we pose is the hypersonic real-time guidance, as well as data fusion and optimal control. Now, as for Earth observation, we have 2 missions here. The first one is the biomass, which is measuring the forestation on Earth. And then the second one is GOCHA, which is its purpose is to measure the gravity field and ocean circulation of Earth. Now, the main problems that these 2 missions are posing, well, the first one is to observe the forestation, or the deforestation in this case. And the need here is to minimize the space vehicle propellant mass or overall mass, and to increase the agility of the space vehicle maneuvers. The current solutions that are used are H-infinity model-based predictive control, and the challenge that we want to impose here is the multi-objective optimization. As for Gotcha, the problem is the measuring of Earth's gravity, and we need to increase the accuracy of the control when tracking, or regulating the planet. The current solution is a PAD cascade in a complex design, and the challenge is the robust optimal control. Now, for space safety, there are two main challenges, let's say. One is the collision avoidance to tackle the space debris issue. So, as you know, as the space around us is getting more and more crowded, there are a lot of collision avoidance maneuver, and the probability, for collision is increasing. So collision avoidance maneuvering is an issue that we would like to tackle, as well as design for demise. As I mentioned before, design for demise is the designing of a spacecraft in such way that it will disintegrate or, well, demise within the atmosphere. So the two main problems that are imposed by that, the collision avoidance itself, and the need here is the real-time prediction of collisions and avoidance maneuvers. The current solution is orbit determination and prediction, and the challenge that we're looking at is the numerical optimization. As for the design for demise, is basically the design of a re-entering spacecraft. And the need is to collocate the components and the materials within the spacecraft in such a way that the spacecraft itself will demise upon re-entry. There is no current solution. Some are being under development, but for the collocation of the components and the materials, there is no current solution. And the challenge that we pose here is the topology, discrete optimization, and prioritization. And for space transportation, we will talk now about the Vega E, which is a small affordable launcher, the Space Rider, which is for reusable launching services, and Ariane 6 for more payload on orbit for less cost. So if we look at the problems here, the main problems are the ascent phases and trajectory to the target in minimum time, minimum fuel, and maximum payload. The need is the optimization of the entire trajectory. So currently, the trajectory is divided into phases. We have the launch phase, the launch by itself, and then let's say if the mission is to go to Mars, then the later parts for the coasting phase and then the DSM maneuver would be, well, usually would be optimized in like separated segments. So so the current solution now is a nonlinear programming and local optimization by segments. And then the challenge that we would like to pose is the global optimization. Another problem is the optimization of non-convergence due to initial guess. And the need here is the automatic configuration of the initial guess. The current solution is manual iterations. So for the initial guesses being configured manually through an iterative process that is not yet automated. And the challenge that we would like to pose here is a Blackbox Optimizer, as we call it, or an automatic transcription methods using perhaps artificial intelligence to provide this initial guess for the optimizer to converge fairly quickly, and thus to avoid the manual iterations of the initial guess. For launchers in general, this is the spice of our business. So the goal for our future is to improve the current rockets and space transportation systems, as well as to develop future launch vehicles. And for that, to provide low access to space and return, we are looking at optimization as the solution, or as a means to improve our launch vehicle design. So now I'm gonna talk about, I'm gonna give a wrap up of all the challenges that I've mentioned for all the ESA missions and maybe suggest a few future activities. Yeah, so for the challenges, I think I mentioned all of them, but here we added a few more. So we talked about the global optimization. So here we would like to obtain true global minima in a very large space search. And their perspectives here are the interval analysis. Another challenge that I've mentioned is the transcription methods. So we would like to translate the optimization problems into algorithms that can be solved. And for that, the perspectives would be artificial intelligence. Another challenge is real-time optimization. So to optimize a problem in real time, that means like every second. The perspective that we're looking at is NLP solvers inside perhaps the motherboards. Multidisciplinary design optimization. So to, as I explained before, to optimize all the spacecraft subsystems at once. And for that, we're perhaps looking at NLP solvers. And here we added also an algebra package to provide high performance and efficient algebraic package. And for that, we're looking at parallelization of this package. Now, I will discuss a bit of future activities and what we're going to do, future opportunities for collaboration. So the first thing I want to do is to announce the ESA handbook on optimization for flight vehicle engineering. This is an idea that we want to bring to life. And the idea of that is to have a handbook of ESA to contain a literature review of the state of the art of mathematical optimization solvers that are used for flight vehicle engineering. The idea is to map all of these optimizers that are available within ESA member states and associated countries, and to have them all in one comprehensive handbook. Together, while performing after this mapping a relative performance analysis of all of the optimizers available. This could be done. This will, of course, will be coordinated by us, but for this we can consider research activity, PhD, or master thesis. So if this is something that is interesting to you, please contact me. We are actually calling for contribution and collaboration. So again, this could be in the form of a research activity, a PhD, or a master thesis, and as well as a working group, which we'll talk about in a second. Okay, so another announcement I would like to make is the MSVE working group, or the Mathematics for Flight Vehicle Engineering working group. And we would like to establish a working group that will, the idea is to deal with the mathematics for flight vehicle engineering in the form of yearly sessions that will be coordinated by us, with the main objectives would be to setting a framework for verification, validation, and comparison of optimization algorithms, numerical methods, and mathematical modeling for flight vehicle engineering. We want to establish a community for knowledge sharing. We want to, of course, review and contribute for the handbook that I have announced a slide earlier for the optimization of the flight vehicle engineering. And of course, to discuss challenges, cases, and problems, identifications to be solved with practical applications. In this working group, based on these challenges and cases that we will discuss, we can also coordinate and form a discussion for future activities. So if this is something you are interested to be a part of, please contact me. Here is my email, orr.cohen@esa.int. We would also like to announce the first workshop on mathematics for flight vehicle engineering. This workshop will also host the working group. Of course, the working group would be restricted only to the working group members. The topics that will be discussed in this workshop is the optimization methodologies, numerical methodologies, and mathematical models. We would like to co-organize it with you, so with academia and industry. The location, of course, is open for proposals, and we are targeting fall 2022. So if you have any ideas or you would like to contribute or to collaborate, again, please contact me. This is my email here. So based on the workshop and based on the working group, we can discuss their future activities to tackle mathematics for flight vehicle engineering and optimization problems. One of those is this example of potential activity, which is a global optimization, which I mentioned before. This is a challenge we are very interested in tackling. And the purpose of this activity would be to develop methodology for global optimization for the comprehensive scenarios, which include the entire trajectory all at once. So as I mentioned before, currently it's done by segments. So it's something that we would like to have a global optimization for the entire trajectory. So this is an example for potential activity. Another potential activity that I also mentioned before that is a challenge for us is to have an black box optimization. And the purpose of this activity would be to solve this issue of non-convergence of optimizers by removing the dependency of the initial guess and configuration of the solver. So basically to eliminate the iterative process that we do to have a good initial guess for the optimizer to converge. So this we think could be done with artificial intelligence and machine learning methodologies with the purpose for it to enhance the performance of the optimizer and increase its robustness and remove the sensitivity for the initial guess. So a quick summary, we discussed the mathematical optimization interest and needs for optimization. And we are calling now for support for the ESA handbook on optimization for flight vehicle engineering. We're calling for the support and participation in our working group for mathematics for flight vehicle engineering. And of course, the participation and co-organization of the first workshop on mathematics for flight vehicle engineering that is planned to take place in fall 2022. So if you are interested in any of those, please contact me in my email. And yeah, I hope it didn't take too long. But yeah, I think that concludes my presentation. Yes, and thank you very much for your attention.
Thank you very much for this inspiring presentation with many challenges. I should also apologize that I forgot to introduce Guillermo Ortega in the beginning, but Orr did that for me, so thank you very much. I'm really sorry for that. But of course, we can now integrate everybody in the discussion. So do I see any questions from the audience in the room, maybe first, or comments? Yeah, there is one, if you come to the front.
Can I get closer so you can hear me?
It's Michael, right?
Yeah.
Yeah.
So wait. Good morning. So I'm Michael Gavet from Artelis. Actually, we developed Nitro, which was in your list. We should probably talk in the future, actually. I had a few questions related to the MDO process that you mentioned and also to the activities of ESA, just to understand. So first question, with respect to the MDO process, the iterative process, this is a human-based process, right? It's not integrated. It's really experts putting their expertise one after the other into every box, and then you're doing iterations like that, right?
Yeah, so in principle, this is the design and optimization process. It's a human, as you said, process. So this is usually kind of done, the design itself is usually kind of done manually by all the experts from the disciplines. However, what we're doing in the section is maybe I'll go back to the slide that I showed it. Sorry, it's a lot of slides. I'll get there. So we're looking at the MDO in 4 main disciplines, which is the performance, aerodynamics, and propulsion and structures. And there we actually have a few solutions for that, for a kind of preliminary quick design for flight vehicles. So the first, wait, too much. Oh, sorry. It's just very slow. Here. So we look at their performance, the aerodynamics, their propulsion, and the structures, and we look at multiphysics design rather than high fidelity. So in this case, we would have a reduced number of disciplines and also less fidelity, let's say, a more simplified models to reduce the computational cost. Yeah, and this is actually, well, aside from the initial guess, this actually we have software, and this could be well optimized, and the iterative process here is done, yeah, using optimization solvers rather than human yeah, iterations done by engineers.
Okay, that's very clear. Thank you.
Okay.
I had another question, if I may. Just to understand with respect to launchers design, the role of ESA and Arianespace. So I understand that ESA is designing the launcher, and Arianespace is like designing the smaller components and building it. Just to understand how does it work actually between the two.
So in our section, we do provide support for the design and for the optimization of the launchers. But how it's done in ESA globally, maybe Guillermo, you could.
Yeah, it is a bit of a combined process. If you are talking about a new invented from scratch launcher, this is done by ESA. Once the launcher it is in a relatively mature state, we pass the design to Ariane Group or any other company, Fiatavio in Italy or any other company, and they implement the design. But the conceptual phases of the design of a rocket are done by ESA, by us. And actually, we are in our section designing a series of new launches. We are already designing the evolution of Ariane 6, which will be called Ariane 7. Without having launched yet Ariane 6. Ariane 6 will be launched next year, but we are already designing Ariane 7.
Okay. Okay, that's very clear. Thank you very much.
Thank you.
Okay, any more questions from both of the audiences? I don't see anything.
I have a question.
Yeah, please go ahead.
Bernard Morin from INRIA. Thanks for your nice presentation. I'm wondering, so you mentioned at several places global optimization, and this is some challenge that you indicate. So what kind of problems for global optimization do you consider, and what type of methods do you apply for this problem?
So I didn't hear quite well, but I hope I understood the question correctly. The question is about the global optimization that we're looking at, correct?
Yeah. You're asking for a problem, an example of a problem that can be the slide that Orr has shown to you for the JUICE mission. The JUICE mission will be launched in 2023. And for us, it has been a big problem because the mission consists of launching from the Earth, arriving at the planet Jupiter, in the planet Jupiter, changing the trajectory and flying by all the moons of the Jupiter planet. So there is no way that we can have a single trajectory optimized at once. So the problem was solved by segmenting this huge trajectory in more than 200 pieces, optimizing the pieces individually and connecting the pieces by hand. So we would like to know if there is a mathematician that can compute one single trajectory at once.
I would just add that even for simpler missions, like for Mars, for instance, what we currently do is we do the modeling till the sphere of influence, and outside the sphere of influence, like we divide it into segments from the sphere of influence to reach Mars. So also that it's something that could be optimized at once rather than divided into segments. Also for the launch itself, for each phase of the mission, it's divided into segments. Here it's not actually integrated by hand, but still if this is something that could be done globally, then it would be beneficial.
So these are optimization on solutions of partial differential equations.
So I just can't hear well. Sorry.
Yeah, I hear that. I heard that relatively well. So the problem is that it is not only partial differential equations; it's partial differential equations that are constrained by inequalities. And the inequalities are actually discrete, not continuous. So you have a mix of practically everything, which is difficult to compute.
Okay, thank you. So what you do is discretize the problem.
What we do is we try to linearize the problem, bring the problem to a relatively easy solution by linearizing, by cutting the problem into pieces, connecting the pieces manually, and not getting the optimal solution, but getting an almost quasi semi-optical, pseudo-optimal solution.
Thank you.
So I have a related question actually. So did I get it right that on every segment you have like a globally optimal solution?
No, in every segment we have a local optimal solution.
Okay.
We don't manage to obtain a global optimal solution even within the segments. And the problem is that it is taking us a lot of time to be able to put the segments together, or at least to choose which kind of best optimal local solution is the best segment to be able to connect to the next one.
Yeah, I see. So then I think second part of my question cannot be answered, but still I try. So is there a chance at least to estimate in some sense how much room there is for improvement? So I understand, of course, you cannot do the global optimization, meaning for pieces, but also for the global trajectory. So do you have an idea if you are talking about a factor of 2 or 10% which may be improved?
We need to have even I could say not a factor of 2 or 1 order of magnitude. What we do is we know that the solution obtained for each of the segments is not optimal. And what we do is once the spacecraft is actually flying, we use commanding from Earth to be able to correct the position of the spacecraft, because we know that the solution that we have computed is far from being global optimal. But there is an engineering trick, and the engineering trick is actually correct the problem that we didn't manage to solve.
Okay, yeah. Good. Yeah, that seems rather challenging. Are there any other questions? I'm looking at the chat. I don't see anything at the moment. Anything else? from somebody in the audience? There's another hand raised. Again, too far away.
Yeah, maybe to keep elaborating on that segment optimization, have you tried something similar to the rolling horizon optimization, like to optimize the first segment, then an overlap of the first and the second segment, and so on and so forth? So you don't have to connect the segments manually?
Well, the segments are relatively long in size. You can imagine the distances in the solar system are huge, and connecting the segments is a problem, but not a huge problem because the length of the segment is huge in comparison with the distance between the connection of two given segments. So it is a process which is tedious, but it can be done manually somehow. The interesting thing for us could be if we don't need to be able to have segments and we can have only one single trajectory. And they will facilitate a lot, actually will reduce the amount of time consumed and the manpower, so which means the money.
Yeah. Maybe also without ending up with a single global optimization, I guess you'll be also interested in reducing the number of segments, wouldn't you?
Yeah.
Okay, thank you.
All right. Michael, Uchwara.
Hi, Orr. You mentioned that sometimes you have problems due to non-convergence, due to bad initial guess. Is that for one particular solver or is it a general problem?
It's a maybe or you want to answer this one?
Yeah, I think here it's a general problem. It's not for a particular solver. The problem is to generate. I mean, to firstly generate the initial guess, because that takes a lot of time and a lot of effort and also a lot of experience with the solvers and with the software that we use. A lot of tweaking to do. So this is something that we currently do manually. And if that process could be automatized, because it's still an iterative process. So we do the initial guess, we get a non-convergence, we go back to the initial guess, we try to improve it based on the non-convergence of the optimizers. And there's certain kind of tweaks and tweaks that you would have to know in order to have it work perfectly. And sometimes even you would kind of get an optimized result, but I mean, from experience, we know it's not the optimized results, and perhaps, yeah, it's because of, well, let's say a bad initial guess. So this whole process of the initial guess is something that we're looking at to solve. Yeah. I don't know.
If I may add on top of the answer of Orr, sometimes we have a very good initial guess and we use Promise, Tropic, Cantos, Nitro, Warp. We use one of the optimizers. We get a solution. We are very happy. Then we go back to the initial problem. We change one parameter or two of the initial problem, and the initial guess has changed and it doesn't work anymore. So we cannot optimize. So we need to find a way to be able to obtain a very good initial guess, which could lead us to a very good local optimization solution quickly.
Just out of curiosity, you mentioned that for some problems you assign two different teams using two different methods. Is there a good experience with that? Do they ever meet with the results?
Well, two different. I didn't understand the question. Sorry.
Yeah, it's on a slide of yours in which you are explaining that the optimization problem is resolved and resolved again and again.
Yes.
And
okay.
I think he was talking about this.
Yeah. So we regularly have well, we cross-check not only between different groups, but also in between us. So we cross-check our models all the time, and yeah, sometimes we don't get the same results, and using I mean we model things differently, and we sometimes we do get the same results, sometimes we don't. So yeah, this is actually something that is very important for us to cross-check between us, not just within the section, but also with others. So I hope it answered the question.
Thank you. Thanks.
Good. Anything else we would like to ask our experts? Maybe I have a last question myself, and this relates to artificial intelligence, which was mentioned in two places. So how would you, do you actually have enough data, or would you have to generate the data you feed into the system you want to train by artificial intelligence, or would they have to be somehow simulated by these very expensive tools you have? How do I have to think about this?
I would say this is a good point. To be honest, I'm not an expert on AI just yet. I believe we do have a lot of amount of data that could be fed in. But yeah, I mean, this is something that we would have to look more into, whether we would have to generate more, or it's something that could be used from the data we already have.
Mm-hmm. Good. So I don't see any urgent questions anymore. So
Maybe a last
thank you
one.
very much. I'm sorry, was there something? Bernard?
Maybe a last one.
Yeah.
Yes, for curiosity. So also, are there other kind of other problems where global optimization is needed in what you have described?
So aside from this particular presentation,
This
you mean?
trajectory, beside this trajectory optimization.
Yeah, so this is only one example. We need where the challenge is the global optimization. We can also, I think I also mentioned in one of my answers, this could also be used for let's say, for Mars missions, for the trajectory optimization of Mars missions, and also connecting the launch phases themselves with the coasting and then the DSM maneuver for either Mars or the Moon, because currently we're using, let's say even for the Moon, for reaching hollow orbits. For that, we would do the launch till the DSM maneuver in one software, or using one particular modeling, and then for the hollow orbits, the NRHO orbits around the Moon, we would use another one, and then we would have to manually connect the two. So yeah, so these are another two examples I could think of.
And another example is the slide in which Orr has shown to you. We need to have global optimization in what we call all at once optimization. There is a slide presented by her in which she was explaining how the propulsion is optimized, how the aerodynamics of the rocket is optimized, how the trajectory is optimized, and how the entire system of the chemical equilibrium of the firing of the thrusters is actually optimized. This one.
Yeah.
So there are several techniques in MDO, multidisciplinary design optimization. One of the techniques we use is all at once optimization, and global optimization. It is needed for doing this. It's not only for the trajectory.
Thank you.
Now, does this answer your question?
Yes, thank you.
Okay. Anything else came up? If not, then I try again. So let's thank again our speakers for this very exciting and excellent talk. And also thanks a lot to the audience for the vivid discussion we had. this morning. Now it's time to have a little break. So enjoy your lunch, everybody, wherever you are. And I think we meet to continue with our program at 2 p.m. again. Goodbye, and thank you very much.
Thank you so much.